Good morning, everyone. Thanks for getting up and coming to this very early presentation. I'm not sure how I got so lucky to draw the 8 a.m. card, but that's what I got. So we skipped ahead on some slides here. Sorry. Okay. So my name's Cam Turner. I am with CoolIT Systems. For those of you who aren't familiar with us, CoolIT is a world leader in direct contact liquid cooling solutions in the data center market. And this project, or this case study that I'm going to present to you is part of the Advanced Cooling Solutions subgroup. So what that is the OCP collaboration on harmonization of the different types of liquid cooling technologies that can be deployed in a data center. I wrote down the charter because I can never remember it, but the overall goal of the Advanced Cooling Solutions project is to create specifications, standards, support documentation, and reference designs which enable global adoption of liquid cooling for data center equipment. So overall, what they're trying to do is make sure that there is a specification in which all the different manufacturers and vendors reside within so that you can use different vendors within the same data center. So what I'm going to do today, I'm going to go over what the objective of the case study was, give a little overview of Project Olympus for the people who aren't familiar with it, go over the different components that we utilized in this advanced cooling solution, the test, the results, and then just a quick discussion about the harmonization effort, and leave a little bit of time at the end for some questions if there are any. So as I mentioned, OCP is investigating different liquid cooling technologies, and we adapted our rack DCLC technology to work with the Project Olympus server in partnership with Microsoft. The overall goal is to ensure, or to determine the performance and efficiency gains used when using direct contact liquid cooling over the standard air solution. The Project Olympus server shown on the screen is part of Project Olympus, which is an OCP infrastructure project. So it covers the racks, the compute, the storage. The scope of our work here was to provide an advanced cooling solution for the compute blades shown up on the screen here. So the setup was two Skylakes, the 8160s, 24, 32 gig DIMMs, a PCIe expander card, and some M.2 cooling in there as well for SSD. We chose to use the Project Olympus platform because it's a versatile platform that's designed around modular building blocks, which fit nicely into the modular building blocks that CoolIT designs in our solution. It's an OCP server project, and that's why we're all here. And the final thing is it is very efficient air cooling. So it was going to raise the bar. It was a challenge for us to come and see how good we could do against the best of air cooling. When you're looking into a cold plate-based system, there's three modules that you'll want to consider. There's what we call the passive cold plate loop, or your in-server hardware. There's the rack manifold, which distributes the transfer fluid from the CDU through all of the different server modules. And then there's the coolant distributions unit, which provides the pumping power as well as the heat exchanging capabilities of the system. In the Olympus server, CoolIT utilized three different technologies of cold plates. We have our RX1 module for the high density heat load of a Skylake, so that's a micro-channeled cold plate. There is also a conduction cold plate that goes out and reaches to the voltage regs to keep them running nice and cool. We have our direct contact memory cooling module. So this is a modular design that supports various DIMM configurations. In this configuration, it's a 4x6 array. It allows for serviceability of the DIMMs without having to remove the cold plate. We also used an embedded tube cold plate, which is just a copper tube running through a chunk of metal, in this case copper. And that's generally what will get used in a lower heat density, kind of a sub 100 watt range. And then the final part to the in-server hardware is the quick disconnect block. So shown here, it is a blind mate quick disconnect in the solution, which I will show you in a further couple slides. CoolIT uses Stobley CGD03 non-drip quick disconnects. These allow for high compensation for misalignment, and they're a full metal design, so are very robust and reliable. So as I mentioned, part of what the Advanced Cooling Solution Group is working towards is an overall specification. So what I wanted to do is take a step back and say, okay, if we treated the server's module as a black box, what would our PQ curve look like here? Where's our operating point? So this was designed for a nominal flow rate of 1 liter per minute. At that flow rate, there's about a 4.5 PSI pressure drop. That's going through 3 millimeter quick disconnects. And it complies with the TCS DECS wetted material list. Now this list has been mentioned in the cold plate calls as a starting point for the wetted materials. And I think it's a great starting point, and that's what we've got for now, so we do comply with that. Inside the server, you'll see on the screen here what the direction of flow looks like. So the way the modular building blocks work, you can have everything in series, everything in parallel, or a mixture of both. In this case, to hit the design points mentioned previous, we basically split the server in two. So you have an internal manifold that one side hits, the coolant comes in, it splits in the manifold, it goes through the first bank of DIMMs, then up through the low density cold plate, back down to the Skylake, and then out through the last set of DIMMs. This solution was developed without having to make any modifications to the motherboard, just some chassis modifications, removing the fans and that sort of thing. One of the things that we were particularly excited about is the implementation of a blind mate manifold here. The Olympus server has an intelligent PMDU that allows for blind mate power and communication so that all service can be done from the front. So it was a must in this design to also provide that for the liquid connection. Again, taking a look at the manifold as a black box, you need to support the total flow rate of each of your chassis, so 42 liters per minute. The pressure drop through here is about 3 PSI, and that's basically just a little bit on the tube and the Stobley 20 millimeter non-drip quick connect. Again, sorry, excuse me. Again, it complies with the same wetted material list. And I also threw the dimensions up here just to show relatively what you'd be looking at. We utilize a 38 millimeter square tube. And then the height is, of course, based on how big your rack is. So what's it look like? Here it is on the left-hand side. There's a picture. The left-hand side of the left-hand picture, you have the PMDU. And on the right is our blind mate manifold connection. So I've got a little video here showing how it works. And you're off to the races. It'll power up, you've got liquid. So the final piece of the building block is the CDU. CoolIT offers a catalog of CDUs ranging from a 10 kilowatt liquid to air in rack all the way up to a 750 kilowatt row-based liquid to liquid heat exchanger. For this test, we decided to go with the benefits of the liquid to liquid, but we wanted to keep it as a rack-based trial. So we went with our 4U 80 kilowatt CHX80. It's easily capable of supplying the flow required, and the total power dissipated in the liquid is about 25 kilowatts in this test. At that level, we see an approach temperature of 5 degrees C. So by approach, that's the delta between the coolant out of the CDU that goes directly to the cold plates minus the temperature of the primary fluid in. Okay, on to the test. So how do we test this? We set an ambient air temperature of 35 degrees C throughout all of it. The liquid flow rate was based on our nominal flow design. We utilized Intel's PTU software to stress the CPU and the RAM. And then some telemetry thermocouples within just to make sure we could record the air and liquid temperatures. What we did vary in this was the primary temperature. So the temperature of the liquid coming into the cold plates is what we emulated here. So W1, if you're not familiar, ASHRAE has a liquid temperature spec. So W1 is max temperature is 17 degrees C. W2 is 27, W3 32, and W4 45. So that's what we varied throughout to see how the performance differed. On to the results. So here are the CPU core junction temperatures. So just keep that in mind. It's not a case temperature, it's a junction temperature. With W1, you're seeing, at the air temperature, you're seeing 85 degrees C. W1, we drop down to 43 C. So that gives us a 49% reduction in your junction temperature. If you have cooled water and you need to get the most out of your system, you can get these CPUs all the way down to 43 C. As you see, of course, as the temperature rises, the liquid rises, so too does the junction temperature, all the way up to 72.5 degrees Celsius, which is still a 15% reduction, and you still have 29 degrees Celsius of margin to T-junction max. So that's a pretty big number, and that's going to allow for us to move forward with the higher density SKUs that are going to be coming forward, the next generation chips. Pardon me? Wattage, these are 205. We are capturing about 550 in the liquid. Here's the results we see for the memory cooling. Again, this is a junction temperature. So at air, you're at about 53, 54 degrees C. When you're running the W1, the chilled water, we see a 44% reduction. And that gradually steps up all the way to the, at W4, it's sitting at about even. So again, just sort of summarizing on the margin to max operating temperature. With air, you're sitting at about a 13 degree headroom. With W1, we can get up to 57 degrees, and W4 up to 28.5. The memory and the lower density cooling, you don't see as big of a jump there, and that's predominantly just because of the technology of the cold plate. If you're just running liquid straight through, not a micro channel, you don't get the same level of thermal resistance. In this case, we actually did it out of CDU. Secondary side, yeah. So at this flow rate, at this design point, the component thermal resistances are shown there. This is, again, thermal resistance to junction. So that would be measured as your coolant temperature, the delta between your junction temperature and your coolant temperature divided by the power in the that's dissipated in that liquid. Server power savings. So what I got shown here is just the server. So with the reduction and removal of fans, so we were able to take 2 fans out, and the speed at which the fans were spinning was reduced by 67%. So you see at W1 a 5.4% reduction from error, all the way up to down to a 3.1% reduction in power at W4. Comparing apples to apples, if we take the power dissipated by the CDU, that adds about 1.5% power reduction. I believe there are more power reductions that can be had in this by optimizing the fan controllers in the BMC, but this was off the shelf. All we did was pull the fans out. So, in conclusion, utilizing the Project Olympus server, CoolIT was able to utilize W4 water and capturing 25 kilowatts of heat of liquid per rack. And as this is just looking at the server, we didn't go beyond that, but it's important to remember that now you have 25 kilowatts of air handling that is off the shelf, off the table. You don't have to worry about that anymore. So you can run this through the piping out to outside your facility using a dry cooler or whatever the data center has. Or it can be reused. So we're starting to see a lot more interest in using that heat that's been transferred out in the liquid for other situations like facility heat or whatever. We were able to reduce the power consumption by up to 4%, and that includes the pumping power. Again, as this deploys larger and you get into a row-based system, that percentage will increase more. You get more efficiencies with the larger pumps. And we were able to maintain a core margin of 26 C to max operating temp on the CPU. I don't have that in front of me. I think it was somewhere around, it was below 55, I think 52-ish. So as part of the Open Compute Advanced Cooling Solutions, we're working together as a group to get to a harmonized specification. What I would see the changes required, just based on the conversations we've had so far, there's an expectation that there will be a universal quick disconnect. So we would need to switch over to that, allowing for our solution to be swapped out with someone else's. Validate our wetted material list versus what the final wetted material list is. Validate performance with our transfer fluid. I didn't mention earlier that we utilize a PG25 solution, but we'll wait and see what the specification calls for, and ensure that we are operating within the PQ envelope allowed within the specification. So my rally cry, the call to action. CoolIT Systems has been working within this OCP ACS group since its inception. For liquid cooling to reach wide-scale adoption, we have to have a harmonized specification. This is going to be a must for the hyperscalers to have multi-vendor support. So I'd encourage everyone to join who's interested in this. I've got a link to the wiki here. There is also a mailing list, and most importantly, there's a bi-weekly call that is on the wiki. It gives the information. And I think it's important. I think it's very important specifically for vendors and users to get involved so that we have a harmonization that people want to support, as well as it allows for the innovation within the space that we've been driving forward over the past, 18 years at CoolIT. With that, thank you for your time, and I can take any questions. I do have a few minutes here. Hi, Dale.
So the distance to maximum temperature, is that the maximum temperature at which the processor shuts down or slows down?
That is the Intel spec T-junction max. So I assume that that's shut down, but I'm not sure.
So it's when it starts.
Well,
so there's a lot more.
yes. Hi. If you have a hose leak, you get liquid in your server. So at this point, we do have a way to detect it, and that can be tied into the overall rack management system. But we've focused all of our effort on preventing that, so on the design principles that keep the liquid on the right side of the tube. Okay, well, if anybody has any questions, I'll be around. Please come up and say hi. Thank you very much.